In this lesson, you will learn how to differentiate and integrate natural logarithmic functions. The derivative of a natural logarithmic function, ln of x, is equal to 1 over x as long as x is greater than 0. The second formula, the derivative of the ln of u with respect to x, this is just the chain rule where I take 1 over u and then take the derivative of u, which is du dx, as long as u is greater than 0. So for number 1, find the derivative of each. Part A, the ln of 2x. So I start by taking the derivative of the ln of 2x, which is 1 over 2x. But then I have to multiply it by the derivative of 2x, which is 2. So when I times this by 2, I get 2 over 2x. The 2's cancel, and so my answer is 1 over x. For part B, the ln of x squared plus 3. So I want to take the derivative, so I write d dx of the ln of x squared plus 3 is equal to 1 over x squared plus 3. But then I have to take the derivative of the denominator x squared plus 3, which is equal to 2x. So that my final answer is 2x over x squared plus 3. For part C, the ln of x. So d dx of the ln of x. So I start by taking the derivative of 1 over what is inside the parentheses. So I have 1 over the natural log of x, but then I take the derivative of the denominator, which is 1 over x. So I multiply this, and I have 1 over x times the ln of x. For part D, ln of 1 over x times the square root of x plus 1. Before I take the derivative, I'm going to use one of the properties of natural logarithms, which is the division property. So when you have 1 divided by x times the square root of x plus 1, I can separate this as two logarithms using subtraction. So I can write this as the ln of 1 minus the ln of x times the square root of x plus 1. And then since I have two functions that are being multiplied, I can separate them, but I'm going to put it in parentheses, as the ln of x plus the ln of the square root of x plus 1. And if I distribute that negative, the ln of 1 minus the ln of x plus minus the ln of the square root of x plus 1. If I did not separate these logarithms into 3, I would have to use the quotient rule and the chain rule together. So by separating them into 3 separate logarithms will make this problem easier when I take the derivative. So I want to take the derivative of the ln of 1, and then I want to subtract from that the derivative of the ln of x, and then subtract the derivative of the ln of the square root of x plus 1, and the derivative of the ln of 1 is 1 over 1, and then the derivative of 1 is just 0, so I multiply this by 0, and then minus the derivative of the ln of x is 1 over x, and when I take the derivative of the denominator it's just 1, and then minus the derivative of the ln of the square root of x plus 1 is 1 over the square root of x plus 1, and I have to multiply it by the derivative of the square root of x plus 1. So the square root of x plus 1 is the same as x plus 1 to the 1/2. So when I take the square root of x plus 1 to the 1/2, it is equal to 1/2 times x plus 1 to the negative 1/2, and then I multiply it by x plus 1's derivative, which is just 1, so that this derivative simplifies to 1 over 2 times the square root of x plus 1. So I can substitute that in, and now I can simplify. So 1 times 0 is 0, minus 1 over x, minus 1 over the square root of x plus 1 times 2 times the square root of x plus 1 is just 2 times x plus 1. When you multiply a square root by itself, the radical symbol disappears, so that the final answer is minus 1 over x minus 1 over 2 times x plus 1. For part E, y equals the quantity x squared plus 1 times the square root of x plus 3 over x minus 1. The directions are to just differentiate. So if you were to take the derivative of this, at first look, it looks like you have to use the product rule in the numerator, the quotient rule with the denominator, plus the chain rule. And that method would work fine, but it would be extremely long. So the reason why this problem is in this lesson is because if you take the ln of both sides of this equation, you have the ln of y is equal to the ln of x squared plus 1 times the square root of x plus 3 over x minus 1. The properties of the natural logarithm will make the derivative simpler. So the left side just stays as the ln of y. But the right side, since I have a product in the numerator and I have division, I can write this as 3 separate natural logs. So I have the ln of x squared plus 1 plus the ln of the square root of x plus 3, and then minus the ln of x minus 1. So I was able to eliminate the product and quotient rules by separating them into 4 separate logarithms, 3 on the right and 1 on the left, and now I just take the derivative of each of the four terms. So I'm finding the derivative of x, but I have the ln of y. So the derivative of the ln of y with respect to x is 1 over y times dy dx, or y prime, equals the derivative of the ln of x squared plus 1 is 1 over x squared plus 1. So I have to multiply this using the chain rule by 2x, which is just the derivative of the denominator, plus 1 over the square root of x plus 3 and if I write the square root of x plus 3 as x plus 3 to the 1/2, when I take the derivative, it is equal to 1/2 times x plus 3 to the negative 1/2, and then times the derivative of what's inside, which is just 1, so that I can write this as 1 over 2 times the square root of x plus 3. So I multiply this by 1 over 2 times the square root of x plus 3. So if I rewrite this as 1 over y times y prime is equal to 2x and then minus 1 over x minus 1 times the derivative of the denominator, which is just 1, and then I can rewrite this as 1 over y times y prime is equal to 2x over x squared plus 1, and then plus 1 over 2 times x plus 3. The two radicals cancel when you multiply them together, and then 1 minus x over 1. Since we're taking the derivative of this with respect to x, we're looking to find y prime. So I have to get rid of this y. So to get rid of the y, I want to multiply both sides of the equation by y, and these cancel. So that y prime is equal to 2x over x squared plus 1 plus 1 over 2 times x plus 3 minus 1 over x minus 1, and then I multiply this by y, and the value of y is the equation that was given to us in the very beginning, so I take this entire fraction and substitute this in for y, so that I multiply this by x squared plus 1 times the square root of x plus 3 over x minus 1. So you could take this a step further by getting a least common denominator inside the parentheses because you're adding and subtracting, and then multiplying by the y that we just substituted in for. But in most cases, this answer is acceptable. So this may seem very long, which it is, but it is still better than using the product, quotient rules, and chain rule if you did not take the natural log of both sides and separate them into 3 different terms. Next, we will look at integrating the natural logarithmic function. So the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c, because the natural log, the domain, are all x's that are greater than 0. So the directions are, for number 2, integrate. So part A is the integral of 2 over x dx, and to integrate this, I'm going to write the 2 on the outside of the integral symbol so that I have 1 over x dx, and so I just integrate 1 over x, which is the natural log of the absolute value of x. And taking this a step further, this 2 in front is also one of the properties of logs. It can be brought up as a power of x so that I have the ln of x squared, and since x squared is always positive, I don't need the absolute value symbol anymore, but I do have to add plus c. So my final answer is the ln of x squared plus c. For part B, the integral of 1 over 4x minus 1 dx. I see that this integral is similar to the form of 1 over x, but before I can integrate this, I have to do a u substitution, where u is the denominator, 4x minus 1, and du is 4 dx. So if I divide by 4, I have 1/4 du equals dx. So I found u, and the derivative of u is in the problem, which is just dx. So I can rewrite this integral as 1/4 times the integral of 1 over u du, and the integral of 1 over u is the natural log of the absolute value of u, and then I substitute the value of u back into the problem. So it's 1/4 times the natural log of 4x minus 1, and then this 1/4 in front is the same as a power. So the absolute value of 4x minus 1 to the 1/4 is the same as the natural log of the 4th root of the absolute value of 4x minus 1. And then I just add the plus c. For part C, this is the first definite integral of 2x over x squared minus 5 from 0 to 2. So So this one is another u substitution because I see that the derivative of u is in the problem. So my u is going to be the denominator, x squared minus 5. du is equal to 2x dx, which is in the problem. So if I rewrite this as 1 over u du, and my limits of integration are from 0 to 2, and I differentiate 1 over u, it's equal to the ln of the absolute value of u, but then I want to substitute u back in, so it's the ln of 2 squared minus 5 minus the ln of 0 squared minus 5 which is the ln. 4 minus 5 is negative 1, and 0 squared minus 5 is negative 5. So I have the natural log of 1 minus the natural log of 5, and the natural log of 1 is equal to 0. So the answer is minus the natural log of 5, and this negative in front can be raised to the top, and this also can be written as the ln of 5 to the negative 1 So I am just left with minus the natural log of 5. And if I put this in my calculator and round to 4 decimal places, I get negative 1.6094. So you can write this as minus the natural log of 5, or minus 1.6094. In Part D, the integral of x squared plus x plus 1 over x squared plus 1. This one looks like it would be a u substitution because I have a fraction. But whenever you take a u substitution, when you find your du, the degree always goes down by one number. So if I let u equal x squared plus 1, the derivative will have a power of x. And if I let u equal the numerator x squared plus x plus 1, the du will also have a power of x. So u substitution fails. So what you do when you have the two powers that are equal, or when the numerator is higher, you use long division first. So first I'm going to use long division on x squared plus 1, and then x squared plus x plus 1, and I take the first term, x squared over x squared is equal to 1, so a 1 goes on top, and it gets multiplied by x squared, and then 1 times 1 is 1, so I'm going to place it underneath the 1 so that my terms are lined up. and then I subtract so that the x squares cancel, and I'm left with x, the 1's cancel, and since I can't divide x squared into x, the long division is complete, where x is the remainder, so I write 1 plus x over x squared plus 1. So by doing the long division first, I now have the integral of 1 plus x over x squared plus 1 dx. I have two separate terms, so I'm going to separate this as two integrals of 1 dx plus x over x squared plus 1. And the reason why I separated it as two separate integrals is because the method of integration that I will use for 1 is different than the method of integration that I will use for x over x squared plus 1. On this integral, x over x squared plus 1, it is now in the form to use a u substitution, whereas 1 dx is just basic integration. So let's start with x over x squared plus 1. I will set my u equal to x squared plus 1. Du is equal to 2x dx. And if I divide by 2, so that the derivative of u is in the problem, I have 1/2 du equals x dx. And so I will rewrite both integrals, 1 dx plus 1/2 of 1 over u du. And if I integrate 1, it's just x plus 1/2 times the ln of the absolute value of u. And if I substitute u back into the problem, it's x plus 1/2 times the natural log of x squared plus 1. So I don't have to put an absolute value around that because the x squared plus 1 is always positive. And this 1/2 in front can be written as a power, and a power of 1/2 is the same as the square root, so it's x plus the natural log of the square root of x squared plus 1 plus c. The last example, part E, is one that involves trigonometry. So the integral of 4 cosine theta over 3 plus 2 sine theta d theta, and we'll integrate this from negative pi over 2 to pi over 2. I'm going to start with the u substitution using the denominator, 3 plus 2 sine theta. So when I take du, the derivative of 3 is 0, and then the derivative of 2 sine theta is 2 cosine theta d theta. And if I divide both sides by 2, I have 1/2 du equals cosine theta d theta, which is in the problem. I have a cosine theta d theta. So I'm going to rewrite this problem, and I put the 1/2 on the outside from the 1/2 du, but I'm also going to bring the 4 on the outside. So I have 1/2 times 4 times the integral of 1 over u du from minus pi over 2 to pi over 2. And I will rewrite this again 1/2 times 4 is just 2. From minus pi over 2 to pi over 2 of 1 over u du, which is 2 times the ln of u and I substitute u back in. So I first substitute pi over 2 in for theta. So I have the ln of 3 plus 2 times the sine of pi over 2 minus the ln of 3 plus 2 times the sine of minus pi over 2. So 3 plus 2 times the sine of pi over 2. The sine of pi over 2 is equal to 1. So this just simplifies to 5. And then minus the ln I have 3 plus 2 times the sine of minus pi over 2. The sine of minus pi over 2 is equal to negative 1. So this just simplifies to 1. So I have 2 times the ln of 5 minus the ln of 1. The ln of 1 is just 0, so it's 2 times the natural log of 5. And if I put that in my calculator and round to 4 decimals, I get 3.2189.